Hello! Today we are going to be talking about the remainder and factor theorems. So our objectives for today are that students will be able to evaluate functions by using synthetic substitution, and students will be able to determine whether a binomial is a factor of a polynomial by using synthetic substitution. Let's get started. When we're talking about synthetic substitution, we're using the remainder theorem. So that's the first theorem we're going to be talking about today. The remainder theorem says that the remainder, when you divide a polynomial f of x by x minus a number, it is the constant is f of a. F of x, so the function equals q of x times x minus the constant plus f of the constant, where q of x is a polynomial with degree 1 less than the degree of f of x. So basically this is saying that whatever your remainder is f of that number. So if we do f of x, our remainder is our final answer. So let's see a problem of these worked out. All right, here's our first example. If we're given this function, we want to find f of negative 2. The first method we can do is synthetic substitution, which is basically synthetic division, which we learned last chapter. So by the remainder theorem, f of negative 2 should be the remainder when you divide the polynomial by x plus 2, because it's the opposite of our x. So what we want to do is set up our synthetic substitution, or synthetic division here. So same thing as when we did synthetic division, negative 2 goes on the outside, and that's always this number right here. Then we're going to take all the coefficients and put them on the inside. So our coefficient would be 3, 2, negative 5, 1, and negative 2. So let's write those in. 3, 2, negative 5, 1, negative 2. Then we're just going to do synthetic division. Bring the 3 down. That's always our first step. Bring that first number down. 2 times 3, negative 2 times positive 3 gives us negative 6. 2 minus 6 gives us negative 4. Then negative 2 times negative 4 is going to give us positive 8. Negative 5 plus 8 is going to give us positive 3. Then negative 2 times positive 3 is going to give us negative 6. 1 minus 6 is going to give us negative 5. Negative 2 times negative 5 is going to give us positive 10. Negative 2 plus 10 is going to give us 8. Now 8 is our final answer because that is our remainder. So the remainder after we do synthetic substitution or synthetic division, that is our answer. So if we want to find f of negative 2, instead of having to plug negative 2 in for x every single time, we can just do synthetic substitution. And f of negative 2 equals our remainder. So f of negative 2 equals 8. All right, so our second method is direct substitution, which is the method we already knew. So anytime you have f of negative 2, right, all we would do is every time we see an x, we substitute in a negative 2. So plus 2 times negative 2 to the third minus 5 times negative 2 squared plus negative 2 minus 2. Now this is just a lot of math, right? That's why synthetic substitution kind of a lot easier than this, but this will work. You can either use synthetic substitution or direct substitution. So here we get 3, then negative 2 to the 4th power gives us 16, plus 2 times negative 2 to the 3rd power gives us negative 8, minus 5 times 4, minus 2, minus 2. 3 times 16 gives us 48, minus 16, minus 20, minus 2, minus 2. Then 48 minus 16 gives us 32 minus 20 minus 2 minus 2. Then we get 12 minus 2 minus 2. And let me bring everything up. And then 12 minus 2 minus 2 is going to give us 8. So f of negative 2 equals 8. So both methods will give us the same answer, and you can choose which one you like better. Personally, I think synthetic substitution's a little bit faster and a little bit easier, but both methods will work. All right, so here's our second example. We're given this function, and we want to find f of 3. So again, by the remainder theorem, f of 3 should be the remainder when you divide the polynomial by x minus 3, or when you do synthetic division or synthetic substitution with 3 on the outside. So set up your synthetic substitution, and let's see, all of our coefficients are going to be 5. Don't forget to put that placeholder 0 because it skips over the x squared term. 2, negative 1. All right, then we're going to bring down the 5. 3 times 5 gives us 15. 3 times 15 gives us 45. And then 47 times 3 gives us 141. We end up with 140. So our final answer, f of 3, equals 140 by the remainder theorem. And that is our final answer. All right, here's another example. So here's our exercises where we want to use synthetic substitution to find f of negative 5 and f of 1/2 for each function. So start by setting up your synthetic substitution. So first we want to find f of negative 5. Set up your synthetic substitution. We've got negative 3, 5, and negative 1. We can also set up the other one as well. So we've got 1/2 on this side. Same coefficients go inside our box. All right, then let's solve each one of these. So bring down the negative 3. Negative 5 times negative 3 gives us positive 15. 5 plus 15 gives us 20. Negative 5 times 20 gives us negative 100. And negative 101 is our answer. So f of negative 5 equals negative 101. Then if we want to solve for f of 1/2, bring down the negative 3. Negative 3 times 1/2 gives us negative 3/2. And here's where we got some fractions, so you need to be careful. 5 minus 3/2 is going to give us 7/2. Then 7/2 times 1/2 is going to give us positive 7/4. Negative 1 plus 7/4 is going to give us 3/4. So if you need to freshen up on those fraction skills, this would be a great time to do that. All right, then f of 1/2 equals 3/4, and that's our final answer. All right, number 3. Just want to do one more example with you on these, especially because there's fractions with this one, and I want you to get some practice and see how these are done. So number 3, set up our synthetic substitution with negative 5 and 1/2. So we've got negative 5 on this side. Our coefficients are negative 1, 3. Don't forget that placeholder 0 because we skip over our x term, and negative 5. Our other synthetic substitution, 1/2. And then we're going to have the same numbers in the box. So negative 1, 3, 0, and negative 5. Now, first step, bring down that first term, negative 1. Negative 5 times negative 1 gives us positive 5. We get 8. Negative 5 times 8 gives us negative 40. 0 minus 40 gives us negative 40. 5 times negative 40 gives us, or negative 5 times negative 40 gives us positive 200. Negative 5 plus 200, we end up with 195. So our final answer, f of negative 5 equals 195, because that was our remainder. By the remainder theorem, that's our answer. Now, over here, we've got 1/2. Bring down the negative 1. Negative 1 times 1/2 gives us negative 1/2. Then we've got 3 minus 1/2. 3 is the same thing as 6 over 2. So 6 minus 1 gives us 5 halves. 5 halves times 1 half gives us 5 fourths. 0 plus 5 fourths gives us 5 fourths. 5 fourths times 1 half gives us 5 eighths. All right, and then negative 5 is the same thing as negative 40 over 8. So negative 40 plus 5 gives us negative 35 over, oops, weird 5, 35 over 8. And that is our remainder. So our final answer, f of 1/2, equals negative 35 over 8. And we always want to see if we can simplify it. In this case, we can't. So we're done, and that's our final answer. All right, on your paper, you're going to see numbers 5 through 10, and that's just a lot of practice on using synthetic substitution to find the values of functions. What I want you to do is go to number 7, and I want you to try to do number 7 on your own. At any time between now and next class, if you feel like you need extra practice, go back and do 5, 6, 8, 9, and 10, and I have the answers to all of them if you want to check. But for now, I just want you to do number 7, so pause your video, do number 7, and when you come back, I'll have the answer written on your screen. So pause your video now and try to do number 7. All right, so you should have set up your synthetic substitution like this. You should have had 4 on the outside, 5, negative 4, that placeholder 0, and 2 on the inside. And then the same coefficients on the inside over here with negative 3 on the outside. You did your synthetic substitution, and you got f of 4 equals 258, f of negative 3 equals negative 169. So if you need a minute to pause, check your work, see if maybe you made a silly mistake, or if you're really not understanding this, raise your hand right now and I'll come over and help you. Otherwise, let's move on to our next topic. The other theorem we're going to learn about today is the factor theorem. The factor theorem can help you find all the factors of a polynomial. The factor theorem states that the binomial a minus a number, a minus x minus a, is a factor of the polynomial f of x if and only if f of a equals 0. So what this means is that if we want to show x plus 5 as a factor of this polynomial, and then we want to find all the remaining factors of the polynomial, we can use synthetic substitution to check to see if x plus 5 is in fact a factor. If we plug it in and do synthetic substitution and we get 0 as a remainder, that means that it is a factor. That is how we use the factor theorem. So let's do this example. Let's check to see if x plus 5 is a factor of this polynomial. So set up our synthetic substitution. Negative 5 on the outside, 1, 2, negative 13, positive 10 on the inside. Then we're going to bring down our 1. Negative 5 times 1 gives us negative 5, negative 3, positive 15, 2, negative 10, and 0. So 0 is our remainder, so yes, this is a factor. So x plus 5 is a factor of this polynomial. So first thing we want to do is take our numbers that are left over, and just like when we learned how to do synthetic division, we want to rewrite what's left of our polynomial. We bring this down 1 degree. This becomes our coefficient in front of our x, and this is our constant. So we want to rewrite this as x squared minus 3x plus 2, and the 0 just goes away. That's what's left. And we know that because we got a remainder 0, negative 5 is a solution, so one of our factors is x plus 5. Now we want to take the quadratic that's left and we want to see if we can factor that to break down our factors even further. So we want to do our diamond. 2 goes on top, negative 3 goes on bottom. Two numbers that add up to 2, or multiply to 2, add up to negative 3 would be negative 2, negative 1. So we can break this down even more and say x minus 2, x minus 1, Don't forget about that x plus 5. And these would be all of the factors of our polynomial. And the factor theorem helped us find them. All right, so in your notes, there's a spot to write this in. Basically, everything we just found on the last page is written out here, everything I just said. So we want to write in this box, and I'm just going to write it down here because it's not enough space. In that line, you want to write x plus 5, x minus 2, and x minus 1. Those are all of the factors of our polynomial. All right, so let's do another example of this. We're given a polynomial and we're given one of its factors, x minus 2. Now we want to find the remaining factors of this polynomial. So we're going to use synthetic substitution to see if x minus 2 is a factor. We need to get a remainder of 0 by the factor theorem to show that x minus 2 is a factor. So start by putting our 2 on the outside, all of our coefficients in here, 1, 1, negative 10, 8. Bring down our 1, we get 2, add them together. 2 times 3 gives us 6, negative 4. Negative 4 times 2 gives us negative 8. And we get a remainder of 0. So x minus 2 is a factor. Then we want to take our coefficients that are left and rewrite what's left of our polynomial. So we get x squared plus 3x minus 4. And then we can't forget to bring down the one factor we know, x minus 2. Oops, sorry about that. My pen is getting cut off, so let's move this up so we have some more space. All right, x minus 2, that's the factor we know because we got a remainder of 0. Now we want to see if we can factor out what's left of that polynomial, or of the polynomial, which ends up being quadratic. So we want to factor it by doing our diamond. Negative 4 goes on top, positive 3 on the bottom. Two numbers that multiply to negative 4 add up to 3 would be positive 4, negative 1. So we're left with x plus 4 and x minus 1. Those are the remaining factors of the polynomial. And I think you should just write x minus 2 as well, even though we're given that that is a factor. List out all the factors together. All right, we're going to skip over to number 5 just because it's a little different, and I think it's important that we see problems that are slightly different rather than doing ones that are the same and wasting time. So let's skip to number 5. It's the same idea. We're given a polynomial and one of its factors, and we want to find the remaining factors. So start by setting up our synthetic substitution. We know x minus 1 is a factor, so put 1 on the outside, our coefficients on the inside. Then we're going to do synthetic substitution, bring down the first term, we get 2, 1, 1, negative 6, and 0. 0 is our remainder, so we're good. X minus 1 is in fact a factor. What we're left with is 2x squared plus x minus 6. All right, that's one of our factors we're left with. We know that x minus 1 is a factor that works, so we're going to bring that down. All right, now we want to take the quadratic that's left and factor it. Now because there's a coefficient in front of the x squared, we've got to do the diamond, multiply a times c. And in our diamond, we're going to get negative 12 on top, 1 on the bottom. Two numbers that multiply out to negative 12 add up to positive 1, be 4 and negative 3. Take the first term, the last term, and these are the terms that are going to go in between. So 2x squared plus 4x minus 3x minus 6. Now to factor this, cut it in half, take out the GCF of the first two terms, which is 2x. You're left with x plus 2. Take out the GCF of the second two terms, minus 3. You're left with x plus 2. All right, and then let's get some more space. What we're left with is 2x minus 3 x plus 2. And don't forget to bring down this x minus 1. And these are all of the factors of your polynomial. And you're done. All right, we're going to skip over number 7 because it's very similar to number 5. And just to save time, once again, I want to show you problems that are a little different. So number 9. Number 9, we're going to set it up using synthetic division or synthetic substitution. So we want negative 2 on the outside. And all of our factors on the inside, 1. Don't forget that placeholder 0 because we don't have an x squared term. 1 and positive 10. Bring down your first term. Negative 2 times 1 gives you negative 2. Negative 2. Negative 2 times negative 2 gives you positive 4. 5. Negative 10. 0. Our remainder is 0, so x plus 2 is in fact a factor of the polynomial. All right, now we want to write what's left over after we factored out the x plus 2. So we're left with x squared minus 2x plus 5. Right? And then we've already decided that x plus 2 is a factor as well. So then we want to take our quadratic in our second set of parentheses and try to factor it. We put 5 on top, negative 2 on the bottom. Now we want to think of two numbers that multiply to 5, add up to negative 2. And we think about it, we list out our factors of 5, just 1 and 5 because it's a prime number, and none of this works. We can't have two numbers that multiply to 5, add up to negative 2. So this is not factorable. Therefore, if we can't factor it, we're done. And this is our final answer. All right, so if you're left with a quadratic that you can't factor, you just leave it like it is. In your notes packet, there's a lot more examples, and I purposely gave you lots of examples in case you feel like you need extra practice. So if you feel like you need extra practice once this video is done, please go ahead and do those problems, and I have the answers to every single question in your notes from today. So if you feel like you need extra practice, go ahead and do those problems and ask. Otherwise, look to your teacher or look to the board to see what to do next, and I hope that you have a great day.